Welcome to Operating Systems Lecture 19. So far we were looking at how the operating system represents and manages processes. So we said that an operating system has a structure called PCB, the process control block for every process. On x86 this is the struct proc that we were looking at last time. And some of the important fields we looked at were each process has a pointer which is of type page directory entry. So this is a pointer which will be a page sized which will point to a page sized allocation which will be the page directory, right, and that page directory will have more pointers to the second level page tables, and those page tables will have pointers to the actual pages. And so this entire structure is private to every process, right? So every process has a private page directory, private second level page tables and private pages, right, assuming we are not doing optimizations like copy on write, etc. I mean, conceptually speaking, each process has a private address space, so it has a private hierarchy of the page table and the physical pages themselves. Each process has a private stack, K stack, right, and once again K stack is allocated from the kernel heap, and it's also a page sized entity in the x86 kernel. And we last time discussed why a page sized K stack is enough. We said the programmer can be careful such that the stack never goes beyond one page, right, and the way that it can do that is basically ensure that the call depth is bounded, that the size of local variables is bounded, that asynchronous interrupts cannot be received while an asynchronous interrupt handler is running, right. So you cannot just have asynchronous interrupts causing trap frames to get pushed, right. So these three things basically ensure that K stack remains bounded, and once again K stack is private per process. And so just to give you some a fact point, a point of data, Linux kernel for example uses a K stack of 8 kilobytes, right, so not really big, right. So x86 uses 4 kilobytes, Linux uses 8 kilobytes, and this amount of stack is usually sufficient for whatever the kernel wants to do. All right, this is yes, there's a question.
So however, if suppose you write a recursive program, then it is like if the programmer, if let's say the designer is just writing a recursive program, then it depends upon the user whether or not what the stack length would be, right? So if let's say I'm writing a simple factorial program and I give him an argument of let's say 100, so if my stack depth is not that much, then would that lead to a stack overflow?
Yes. So let's say a programmer writes a recursive program, let's say just simply writes a recursive factorial program, and your stack depth is limited by whatever you have said here, let's say page size, then will your stack overflow? Yes, that will overflow. So what does that mean? The kernel developer should never write a factorial program inside the kernel, right? There shouldn't be a function which is recursively going to unbounded depth depending on the user input. Shouldn't be possible, right? A user program also does not have an infinite stack, right? So even if you write a user program has a larger stack than the kernel, the K stack, but it's not infinite either, right? So even if so there is actually a limit to how much recursion you can do even in the user space, but it's much larger than what you can do in the kernel space.
Sir, we said that we disable interrupts while we are handling the external interrupts. So while we are handling the external interrupts, can a process switch happen because of timer interrupt?
Okay. Well, I said that we disable interrupts while we are executing an interrupt handler, and when the interrupt handler is running, can you actually switch processes, right, or switch the kernel stack and then you can move there? Yes, you can. All right, but the switch will not re-enable interrupts. Interrupts will get re-enabled only when you go back to user mode.
But then switch happens on the timer interrupt.
Sure. So what will happen is, let's say process P1 is running and an interrupt occurred. Process P1 starts running in kernel mode on the kernel stack with interrupts disabled. The kernel stacks get switched. The new kernel stack, P2's K stack, is still, so P2 starts running in its kernel mode on P2's K stack, but still the interrupts will be disabled.
So isn't the timer interrupt disabled?
It will be disabled for the duration of the switch, right? And then as soon as you go back to the user mode, you're back again, right? So how do the interrupts get enabled when you go back to the user mode? because when you actually do return from trap, so you pop off all the registers and then you execute the IRET instruction. And recall the IRET instruction pops off E flags, right? And so the flag in E flags which indicates that the interrupts are disabled or enabled gets reinitialized based on the user value. And so now when you're in user mode, you're executing with interrupts. Whatever the in general you will be executing in user mode with interrupts enabled, right? Of course, now the user, if it makes a system call, then the system call need not disable interrupts. But if another timer interrupt occurs while you are executing in user mode, then again you will execute with timer interrupts disabled, right? Interesting. So another question I have for you: should a user mode program be allowed to disable interrupts? No, because if a user mode program is allowed to disable interrupts, he can just take control of the system, right? So how does the architecture ensure, or how does the OS developer ensure that a user mode program cannot disable interrupts? So the CLI instruction, that's the only way to modify the bit of the E flags, is a privilege instruction. And so if the user ever executes that instruction, what will happen? An exception will get thrown, and the kernel's exception handler will get called, and the kernel exception handler may just kill the process for what. Okay, right? There's another question? Okay. All right. Okay, so that's KStack. And now trap frame. So we said that each PCB on x86 also has this pointer toward trap frame. And this trap frame is basically nothing but it contains all the registers in user mode just at the time of entry to the kernel, right? And this is a nice thing to have, because later if you want to refer to these registers for either arguments or anything else or return value, then you can do that using the trap frame. And trap frame is always pointing within the stack, within the KStack, right? In fact, okay, we're going to see exactly where it will point all the time. A trap frame for a saved process is always valid. A trap frame for a runnable process is always valid. A saved runnable process is always valid. The trap frame for a running process, a process that's running in user mode especially, is not valid, because it will get overwritten as soon as you come from user mode to kernel mode. So whatever the contents, completely immaterial. All right. And then we said there is another pointer called context. And this context is basically saving the state of the kernel thread of that process. So when you came into the kernel mode, you executed some functions, and then at some point you called the switch function, which we saw last time. And the switch function is going to create this structure called context, where it's going to save all the callee saved registers and the return address, that's the EIP, on the stack, point context to that location, and then switch to another process's context, right? So if I look at the stack of any process, KStack, so let's say this is the KStack, I'm calling this the bottom. This space from context to KStack is not used, right? And this is the top of the KStack. So this is, what top is equal to bottom plus 4096, 4 KB, right? So we know that it's a fixed sized stack. So you k-allogged a stack, so that's what you got as a pointer to KStack. Then you said plus 4096, that's my top. That's what you're going to feed into the TSS. And so in every trap, all these values are going to get pushed first by hardware and then by your interrupt handler instructions. And that's where you want to set up your trap frame pointer, right? So this is the trap frame pointer, and you can look at all these fields from the trap frame. In fact, you didn't really need the trap frame pointer, because you already know, if you know KStack, you can calculate TF by simply saying KStack plus 4096 minus whatever is your size of trap frame, right? It's always at a constant offset from KStack, but just for convenience, let's just have a separate pointer in the PCB, not a big deal. Also, we said that so these values get pushed by the interrupt handler, and the interrupt handler ensures that the next sort of return address should be this address of this function called trapret, right? And we said that one way to do that is just make sure that arrange it as a function and then make a call to wherever you want to do. So the return address automatically becomes trapret, and then you will call some functions which will have their own local variables and return addresses, etc. And finally, somewhere you will call switch, right? So as soon as you say call switch, the return address of the function which called switch gets pushed as the EIP, right? And then the next 4 callee saved registers get saved by the switch function itself, and that's it, right? That's where you have switched. So at this point of the stack, you actually perform the switch, right. So for any runnable process, this will be basically the structure, context will be pointing here, everything here is completely unused and everything here is meaningful. And when I am going to switch to the other process's context and I am going to pop these values to refresh my kernel, to reload my kernel state, and then the kernel is going to do something, and then eventually it is going to pop these values to reload the user state. Okay, good. Right. So today I am going to talk about, we are going to look at how XV6 creates the first process. Right. So basically what it's going to do is that it's going to allocate a page directory and it's going to initialize the address space to point to some code that the kernel wants to execute first in the user mode. That's one thing it will do. Then it will allocate a K stack and it will organize the K stack as though the process was just switched out, right. And then it will add the it will initialize the PCB to point to all these things, K stack and page directory and other things, and it will just add the PCB to the list of schedulable processes. In other words, it will just mark the PCB runnable, right, and then it will call the scheduler, and the scheduler will just go through the list, pick up any runnable process. In this case it is the only runnable process because it is the first process that you are creating, and you will just pick it up because you had set up the stack in exactly the way any other process would have been had it been switched out. It just starts running in the normal way, right. Okay. So let us look at that. So we are going to look at this function called user init on sheet 22. So this function is called from main after other things have been initialized, and user init is going to set up the first user process, right. And what does it do? It makes a call to this function called allocproc. What is allocproc going to do? It is going to allocate a PCB, okay. It's going to allocate a PCB and it's going to, let's see what exactly allocproc does. It's going to allocate a PCB and it's going to allocate the K stack of that PCB, and it's going to initialize the K stack with the trap frame, etc. All right. So let's look at allocproc first. So on the same page there is allocproc, line 2205. All it does is it assumes that there is a global variable called ptable, this table of all the processes. It iterates over the table, right. So I have been saying that it's a list of PCBs, but XV6 implements it as an array of PCBs, right. So it just says that there is a limit to the maximum number of processes you can have in the system, that's nproc. So it's just going to go over this array of processes, and if it finds that one of those processes has a state unused, then it's going to do other things. If it couldn't find anything that was unused, then it just says I couldn't find anything. And so what should happen is basically, if the first process was not being able to get created, then you should just return an error that you couldn't boot properly, basically. If you came here because of fork, then you would just return a -1 value to the fork, right. Okay. So at this point you have allocated, you found a process that you found space for the process, you found space for the PCB, you initialize its state to embryo. So you initialize it, so from unused you initialize it to embryo. The reason you initialize it to embryo is because because XV6 is a multiprocessor system. So once you have taken a you have pinned one particular process block and said that I want to use it, you want to basically mark it such that nobody else starts using it after that, right. So exactly how this works, etc., will be the discussion of concurrency and locking, which we're going to do next, but let's just notice this at least, right. Okay. Then we assign a PID to this process. So there's this global variable called next PID, which is, let's say, initialized to 1 or 2 or whatever, and each time you create a process you just increment PID and just put it in this variable, right, and then you release a lock. We're going to talk about locking later, but let's just not worry about it now. All right. Then we allocate a stack, K stack, right. Once again, if you couldn't allocate a stack, you return an error, and you reset the state of the process to unused. So you didn't actually do anything, and fork failed. And then you basically initialize a stack pointer. This is a local variable sp to K stack plus K stack size, and in our case K stack size is 4096, right. And then from there you make space for the trap frame, So size of star p pointer over tf is basically saying size of struct type trap frame. So basically say, you know, that's the location where you're going to point tf to, right. As I told you that, you know, k stack and tf are always at a constant offset, you don't really need to store it, but it's more convenient to store it. Okay. All right, and then what he's doing is he's basically saying let's decrement let's push the address of this function called trapret, right. So we saw this function called trapret that just pops all the registers and then calls iret. So it just pushes the address of this trapret function into the stack. That's what it's doing. So sp minus is equal to 4 and star sp is equal to trapret. That's just pushing trapret into the stack, and finally it's making space for a context structure, right. So it just makes space for a context structure. So size of star p pointer over context. So let's I'm going to show you this context structure. Context structure is nothing but those 5 registers, 4 callee saved registers and 1 instruction pointer EIP, right. So all those 5 registers space is created for, and you make context point to that location. Is context also always at a constant offset from k stack? In this case it is, right, because you can say that context is always equal to k stack plus k stack size minus size of star tf minus 4, and that's minus size of star context, and that's where context is always going to point. But in general, is context always at a constant offset from k stack? No, right, because you may have some call chain between trap frame and actual call to switch. But in general, actually is the trap frame also always at a constant offset from k stack? Not necessary, because as the first trap frame will always be at a constant offset from the k stack. But if there was another trap while you were executing in the kernel, then that trap frame can be anywhere in the k stack, right. So actually, you know, trap frame is not the tf variable is not redundant. It's basically telling you the location of the last trap frame, right. So it's not necessarily at a constant offset from k stack. It's actually, it could be somewhere in the middle. All right. So this is context, and then you so here what he's doing is he's zeroing out the context structure, except that the EIP of the context is set to the address of forkret, right. Okay, I'm going to discuss this very soon, but look at this first. I didn't really initialize the trap frame, right. I only allocated space for the trap frame. I didn't say the trap frame's register EAX should be this value, or CS should be this value, or SS should be this value. They're just, you know, they're just random values here. I just allocated space. So this function called allocproc is not initializing the trap frame, it's just allocating space for the trap frame, and whoever is the caller is supposed to fill values in the trap frame. So in the case of user init, we are going to manually fill some values. In the case of fork, what's going to happen? The parent process's trap frame contents are going to get copied into the trap frame, right. So the allocproc is not doing any initialization of the trap frame, it's just allocating space, and the caller, depending on whether it was a fork or whether it was a user init, it's going to initialize it differently. Okay. All right. So context also has not been initialized, except there's one value in context that was initialized, that's the EIP. All other registers have been initialized to 0, which has no meaning really. All right. Let's look at context once again. Let's look at sheet 20. This is the declaration for struct context, and struct context has these 5 fields, which basically look they are integer fields, and they have been named on the registers that register values or register names: EDI, ESI, EBX, EBP, and EIP. Right. Notice that these fields occur in the inverse order in which they were pushed in the switch function. All right. So for example, you've pushed EBP first, so that comes last. In fact, you pushed EIP first, because as soon as you call instruction, the return address got pushed first. So EIP is last, then you pushed EBP, that's second last, EBX, ESI, and the last register you pushed was EDI, so that's the first, right. So it's, you know, if you look at this stack, you pushed in this order and you pointed context here, and so context basically, you know, if I was to get the EDI value, that's the first field of context, and if I were to get the EIP value, that's the last field of context. right? And so what I have done in user init is basically I have set up all these 4 to 0, and I have set up EIP to a function called forkret, right? And so this is a special case where switch wasn't called by a function, but switch, right? So switch wasn't called by a function, but we just initialized it as though switch was called by a function just before forkret, right? So that, you know, when it actually starts running, it starts running at this function called forkret. So in this diagram, basically what I have done is so this is for a general process for any time, but for user init, what I have done is basically instead of any general EIP, I have set it up to forkret, right? And actually there is nothing here, so this is both short circuited. So the next word after forkret is trapret, if you look at how alloc_proc worked, and then everything above it is trap frame, which is completely uninitialized values at this point, right? So my stack is basically this large, which has 4 registers, forkret, trapret, and the trap frame. That's what alloc_proc does, right? This is the same function is called even on a fork, so that's how it initializes a new process, right? So this name forkret basically means that that's the first function you should call for a process that just started after fork. So let's look at the so first, before we look at the forkret function, let's look at user init after alloc_proc. So I have called alloc_proc here, right? And then I set up some global variable called init_proc to p. Let's ignore that for now. And then I say p. So alloc_proc didn't allocate a page directory, right? So the caller of the alloc_proc is supposed to initialize the page directory. In the case of a fork, you will just copy the page directory. In the case of user init, you are going to initialize the page directory, and the first thing you have to do is initialize the page directory such that all the kernel mappings get created. Recall that setup KVM creates all the kernel mappings above kern base. So for example, it creates mappings from 0 to kern link, and then, you know, for all the heap, and then for all the memory map devices on the top, right? So that's setup KVM, okay? And then it so at this point the page directory basically has all the kernel mappings, but has absolutely no mappings from 0 to kern base. And then there is this function called init_uvm that creates mappings for the user side, and what it's going to do is it's going to create a mapping for the addresses 0 to something. Say 0 to, actually the first process is assumed to be less than the size of a page, so it just creates a mapping for the first page 0 to page size, and fills that location with the value of this array, you know, binary init code start and binary init code size, okay? So this array is pasted at location 0 till page size, okay? So what is he going to do? He is going to paste, so the kernel already knows that this is the first process I want to run, so he is going to take that process, paste at location 0, set up EIP to point to 0, the user's EIP in the trap frame, and is going to just leave it in the scheduler, and the scheduler is going to start running that process immediately. Yes?
So can you again explain what binary init code start is?
Okay, so what is binary init code start? Binary init code start is some global array in the kernel. It contains the contents of this array are basically the code that should be executed in user mode, okay? So once again, the binary init code start is an array, and the contents of this array is the code that should execute in user mode, right, starting at the first location, 0th byte, okay? And so the linker scripts have been arranged in such a way that there is some code that has been created. So what the compiler will do is it will compile this code. The code is written in assembly, let's say, so it's going to compile that code, it's going to get some binary representation of that code, it's going to take that code and put it in the array, binary init code start, and now this user init function is going to take contents of that array and put it at location 0 till page size, and set up my trap frame accordingly, and that's my first process. so let's look at the code that's going to run in the beginning. All right. So what are the contents of binary netcode start? The contents of binary netcode start are in this file called init.s. Initcode.s, that's on sheet 77. So that's initcode.s, and these are the instructions that are going to get executed when the first process actually gets to run. So all it's doing is it's pushing an argument argv and pushing. So these are global variables argv and init that contain the name of a file that needs to execute, and ultimately it's just making a call, system call called sysexec. So it just calls the software interrupt and it's going to make a exec system call. So the first code is going to do nothing but just make us an exec system call on this file name called init with the arguments called argv, and these init and argv are global variables that contain strings, which is the name of the file that needs to get executed, and argv is the name of the arguments that need to get executed. Okay. So all it's doing is making the exec system call. So the first process is going to make the exec system call, and the assumption is of course that by the time the first process gets to run, your interrupt descriptor table has been set up, so system calls can be actually executed. Make sense?
We haven't any. Where is this file stored? Actually, we don't have any file right now, right?
So I mean, this is just code that gets compiled by the compiler, right? But it doesn't get linked to your kernel, right? So the linker is going to just look at the assembly, the binary code of this particular code, and it's going to paste it in this array called binary netcode start. How it happens, let's just ignore that.
So it won't execute it actually.
It won't execute it. Right? So the kernel will never execute this code. The kernel looks at this code as data that it puts into the address space of the first process. That's all. For the kernel, this code is just data. Okay, so let's look at this again. Let's see. Okay, so we're talking about user init that's going to create the first process, right? So what's going to do is it's going to allocate a new PCB. It's going to initialize a new page directory, okay, and it's going to paste the contents of the first program that it wants to run into this page directory, into this address space, okay. And that's it. And I'm just showing you what is the code that executes in the user mode for the first process. The code that executes in the user mode for the first process is just making an exec system call, and then making an exit system call after that, I guess, right? So xv6 is a Unix-like kernel. It implements Unix system calls. We have seen Unix system calls, we have seen fork, we have seen exec, and xv6 also implements fork and exec. And so the code, the first process's code is going to use this system call called exec to start running something, and it's going to exec this program called /init, and init is going to execute, let's say, the shell or something, right? Okay, anyways, so it's not important to know exactly how this is being done, but let's just come back to user init, sheet 22. So let's look at what happens at this point, right? Let's look at what happens at this point. So if I were to draw the address space of first process, okay. So I'm just creating the first process, and I'm now saying let's look at what this address space looks like, right? So we have seen what an address space of a process looks like. Well, it just looks like this box going from 0 to 2 to the power 32 minus 1. This is the virtual address space, right? And what after setup KVM, that's kernel's virtual memory, the address space is going to look something like this. It's just going to have a mapping from kern base for k code, k data, k heap, and so on, right? So that's what setup KVM is going to do. It's going to create all these mappings in the address space. So this is after setup KVM, and then there is this function called init UVM. After init UVM, and init UVM basically takes arguments as an array called binary init code. So after init UVM binary init code, what's going to happen is it's going to paste binary init code here. Okay, that's what it's going to do. So in the address space, it's going to paste binary init code here, and it's going to set up the EIP to 0. So the first instruction that gets executed is whatever there was in binary init code, right? And what I just showed you is that the first instruction that gets executed is just making an exec system call, right? So what will happen is that the control will come here. It's going to make an exec system call, and the exec system call will proceed just like it's supposed to proceed. It's going to replace these contents with whatever is the contents of that file. Load that file into these contents. Okay, is this clearer? Right. So this is binary init code. So that's what init UVM is going to do, and I just showed you the code for binary init code, which is just going to exec the first process. Good. So I say init UVM, that's going to create that mapping. So there's a field in the struct proc called size. What's the size of this process? So this first process has a size of 1 page. That's all. So this, the kernel just knows that the binary init code is less than 1 page, so it just creates a size of 1 page. So size is equal to page size. Finally, it's going to start initializing the trap frame. Right? So I said the trap frame was left uninitialized by alloc proc. So in this case, it's going to start initializing the trap frame. So it first zeroes out all the contents of the trap frame. So all the registers are 0 by default, except CS is pointed to the user's code segment, right? Similarly, DS is pointed to the user's data segment. Why can't we have done, if for example I had done it to the kernel's code segment, then what will happen? So if I had, instead of seg u code, written seg k code, then when I would have transferred to the user, the first instruction of binary init code would have executed in kernel mode, right? You don't want that, right? Because those programs are going to take user input, which is untrusted, and you don't want. So it's going to take a user program and going to call exec on them and all that. So if all those things start executing in kernel mode, you are in bad shape. So you want that those things should execute in user mode, and that's what you're initializing the segments to user mode so that they execute in unprivileged mode. Okay, and then you initialize other segment registers. You're just copying DS to ES and SS. E flags is initialized to FL_IF. What this means is that the interrupt flag is enabled in the user mode, right? So that's what it means. And ESP is initialized to page size. What does that mean? What does that mean? ESP will, or let's say I allocated 1 page. So this is page size. This is page size, and the first few bytes were taken by binary init code, and you initialized ESP here. So binary init code needs some stack to run, and so you initialize the stack at page size. That's what he's doing, and he's just going to use 3 or 4 words in the stack to just call the exec system call, and it's going to initialize the EIP to 0. That's user's EIP, user's EIP and user's ESP. Right? And how is he going to do it? He's just going to change the values in the trap frame for the registers ESP and EIP. ESP is initialized to page size, and EIP is initialized to 0, beginning of initcode.s, and you set up the state to be runnable. Moment you set it to be runnable, a scheduler can pick it up and start executing it, In this case, I'm executing the first process, so there are no other CPUs, let's say, enabled. But the next thing the main is going to do is it's going to make a call to scheduler, and scheduler is going to start picking processes. Question.
Sir, isn't the address 0 that we are setting to EIP invalid, because generally address 0 is not.
Okay, so question is, I said last time that address 0 is usually unused or unmapped, so that you can do this, so that malloc cannot return 0 as a valid value, right? Well, I mean, actually, it's not complete. So, my statement is not completely accurate. It's just that the address space is organized in a way such that malloc cannot return 0 as a valid address. So, in this case, also malloc will not be able to return 0 as a valid address, because that 0 address has the code mapped to it. Heap is not mapped to 0, right? So, basically, the address 0 should not be part of the heap. That's good enough. And in any case, this program is not going to initialize the heap or initialize malloc or free or anything of that sort. So it's okay. Right? This is just a special program. That's just a convention for usual programs. Right? In fact, even this function could have used malloc and free, because 0 is not part of the heap. Even though 0 is mapped, 0 is part of the code. So it can never be a part of the heap. Okay, all right, okay, and we have the first process. So we initialize the page directory, we pasted some contents into the address space, we initialize the trap frame, we initialize the case stack, we initialize the trap frame, we initialize the context, and we have a PCB which is full, we set its state to runnable, and that's it, and we let the system run, and the first process is going to get to run. The first process is going to call an exec, that's going to execute some program. That program is going to, let's say, initialize its file descriptors and call fork depending on what command you give on the keyboard, on the standard input. Right? And so your first process is running after that. Right? So just for completeness, let's also look at other things in the proc structure. So here is the proc structure. We have looked at case stack, we looked at PageDir, we have looked at state, right? So the state can be one of embryo unused. Unused basically means that this particular PCB is not being used, because it's an array. That's how you basically check whether something is used or not. Embryo we have seen, runnable we have seen, something that's runnable. Then there's something called running. Why do I need a distinction between runnable and running? So if a process is already running on some CPU, and then another process wants to schedule another process, then this process should not be a candidate. Right? If a process is already running, then that process should not be a candidate. So one process cannot run on two CPUs simultaneously, not allowed. Right? So that's why you need a distinction between runnable and running. Zombie, we know what a zombie process is. So because x86 does the same zombie semantics as Unix, so it needs zombie. So basically, if a process is executed but its parent hasn't called wait on it, if a process is in zombie state, what do you think will happen? PageDir will remain allocated, or should be freed? Freed. Yeah. So everything will be freed actually. PageDir will get freed, case stack will get freed, TF and context are meaningless. Just whatever is the status exit code of that particular process, that needs to be. But I don't think even x86 even implements exit code, so it actually doesn't need anything for that matter. Right. I'm not sure actually.
Pointer to parent also be stored.
Right, and then there is a pointer to parent. Right. So that's again you need it for this exit wait semantics. Okay. Then there's a PID, parent, trap frame, context we have discussed. Let's look at channel later. Killed also, let's say, let's look at later. This is an array of open files. Struct file star O file, number of files, maximum number of files. So this is your file descriptor table that we discussed in the first few lectures, right? So I said that every process has a file descriptor table, and a process can call open, read, write, close, dupe, all these system calls. So x86 implements all these system calls, and this is the file descriptor table with which it implements these system calls. And it has the same semantics that's going to start from the beginning and search for the first empty file descriptor and assign it there. when you make an open call or something like that. Then there's a variable called current working directory, CWD. Why do I need the current working directory? Recall that the child process on a fork inherits the current working directory of the parent process. That's why when you type ls on your shell, ls knows whose contents to display. Display the contents of the current working directory in which your parent was living, right? So that's so CWD gets copied on fork from parent to child. And if you ever want to find out where am I, you just look at you just say look at proc.cwd. So if ls wants to look at the current working directory, it can do that. All right, and then process name, that's for debugging purposes. Right, so that's basically your struct proc. Okay, then let's look at the main function once again. Yes.
Why is the type volatile in PID?
Okay, why is the type volatile? What does volatile mean? I'm going to discuss that later. Let's just skip that for now. I'm going to discuss that later. Okay, and this is the main function. Recall that we had already seen how control transfers to main, and then this was the heap getting initialized to first 4 MB, the kernel's page table getting initialized, then everything started getting initialized, and at this point you initialize the heap to till fizstop, and this was user init. So as soon as you initialize the heap to fizstop, you call user init, so the first process gets created, and after that you call this function called mp main, let's say multiprocessor main, which let's say other processes are also going to call. And what multiprocessor main does is it just initializes the IDT, right? So just loads the IDT into the IDTR, and then calls the scheduler. Right? So notice that in this case the IDT was initialized after the first process was initialized. It's okay because the first process was initialized, but it can only run after the IDT has been initialized, right? And so IDT gets initialized, and then you call the scheduler, and the scheduler is going to go through the process table, pick up one which is runnable, and call switch to it. So let's look at the scheduler. Okay, so that's sheet 24. That's the scheduler, and scheduler is running on what stack? The scheduler is running on the same stack on which main was running. Right? So there's just one initial stack on which the scheduler is running, because you just made a function called to scheduler. But what it's going to do is so let's ignore the locking, but it's going to go over the process table, and it's going to find if it's not runnable, then you ignore it, but if it's runnable, then you fall through, and you call this function called switch UVM to P, right? So what is switch UVM going to do? Firstly, it's going to load the P's page table into CR3. No problem, because P's page table also has mapping for this kernel, so you can just switch from, so switch UVM has changed the address space right there, right? So it has changed the address space. It will also set the stack, initialize a stack pointer in TSS segment, right? So it will also initialize the stack pointer of the new process. So it will take the ESP value of the new process and put it in the TSS segment, so that when you are going to transfer control to this process and there was an interrupt, then the right stack gets loaded. You shouldn't load, because right now you are executing on the kernel on the scheduler stack. Now you want to execute on the process stack, right? So it's also going to load the value into TSS, so that next time there's an interrupt, it comes into that stack. Set up the state to running, and then call this function called switch that we have seen last time, and the switch is going to switch from the scheduler stack to that processor stack, and actually it's never going to return, right? It's not going to return immediately, it's going to return at the next switch. So the scheduler calls switch, but never returns from here, right? Or doesn't return immediately at least. The processor stack has been loaded, so the process stack returns. So the function that will get called after this is, in the case of first process, what's going to get called? Forkrate, right? So immediately after this, forkrate gets called. You don't return here, but it's forkrate that called, and it's called on the new stack, with the new stack being loaded into the TSS and with the new address space. Let's look at forkrate, sheet 25. Well, forkret does nothing. So this is line 2534 is where it's going to start executing, and this is just a global variable, static variable. So let's ignore this. It just releases some lock basically. So let's ignore that also. It initializes some things, and then it returns to the caller. For the first process, who is the caller of forkret? Trapret, right? So as soon as it calls return here, it's going to get back to trapret. Okay. Recall that the stack was set up in such a way that it looks like the trapret called forkret, right? Because you had trapret's EIP and then you had forkret's EIP. Right. So now forkret gets to run. So forkret could have pushed some things on stack, but it's also its responsibility to pop those things from stack, calling conventions, and then it's going to call ret. So it's going to return to trapret. And trapret is going to do what? It's going to pop off the trap frame and return to user mode. And trap frame was initialized by our user init function. So great, we are running our first process. Okay, so finally let's just look at the init code function on sheet 77, so which we skipped. So let's say it's just going to make a system call called 6exec, and it's going to call actually init.c, and init.c is just going to initialize its standard output and standard error. It's also going to initialize the standard input, and it's going to execute the shell inside. So it's initialize the standard input, standard output, and standard error, and then it starts running the shell. The shell just takes in a command, and so here it's just calling exec sh, and sh is going to take in command and start executing it. Right? So that's what's doing. So that's how you get a shell when you run the x86. Okay, let's stop there.